Okay. So, making talk. 3, 2. All right, everybody, welcome to 61C Lecture 6. Woo! Friday! It's Friday. So, the news today, we've got robots that learn from us. This is outstanding work by Peter Abeel. Many of you might know him, taught 188 recently. He's an EE faculty. I think he's on the verge of EE and CS. I think he's part of both of those pieces. His recent work has been featured on YouTube and lots of press for the towel and sock folding robot. And that's pretty exciting. And now he's working on having robots be apprentices, where robots would learn from your actions and just watch you how to do something and then can be able to simulate that. Is there a question? Is my mic on? My mic's on. Thank you. So anyway, cool stuff by Peter Abeel. He was interviewed in the tech. So if you go to this website, there's a little mini interview of him. You can see his towel folding robot. It has kind of millions of hits. It's really great stuff, and we're glad to have him on board. So we are in a whole new section. We're learning about MIPS. MIPS is a fundamental building block if you're understanding how the top connects with the bottom, how you go from scheme all the way down to electrons. MIPS is right in the middle. Scheme to C is just you can write a scheme interpreter in C. That's easy. C to MIPS is the next connection, and we're learning about that. I'm showing you MIPS by showing you how C maps to MIPS. So we'll learn more of that today, and then later we'll show you how MIPS maps to ones and zeros, then how we take those ones and zeros and build a machine that is able to interpret those in a semantically understandable way, and build a machine that actually is able to chunk and successfully do an add. So if I say add with these things, the machine will actually do that addition, and you'll see how to build that here. This class is the only place you'll learn how to do that. Good stuff. We've seen 3 new instructions, and I have one exception. So I gave the adds and subs, and that was fine. It was an RRR instruction. Then I gave you the I. People said, how about a constant, Dan? I said, all right, here's a constant. And I had to apologize once because I have one exception, which is the immediates. So we saw that. We also saw why we don't have a sub-I, because you know that the immediate can be negative. It's interpreted as a signed integer. I've shown you, I believe, 16 of the normal registers plus 0, that's 17. We'll learn some more today. So the most important thing you understand is that all arithmetic operations and logical operations happen on registers. They read 2 registers, they write a register. And maybe there's a constant in there in addition, but it's always writing registers. It's never about memory. But Dan, my data lives in memory. How do I get it from memory to registers? That's what we're talking about today. Okay? So C variables are registers. You can think of any local variable, int x, as living in a register. Just assume it works that way. But how about an array? The large array is... Say that for Mike. Say that for Mike. Okay. Well, Mike comes. He's got to sit there. Okay, but Mike's got to sit there. Okay. So, memory is one of the 5 pieces of the computer, and memory is where our stuff lives. If I say int a of 4, then what does that mean? That means I've got 4 integers in a row. Where does that live? It doesn't live in registers. So it lives in memory. Okay? I think of memory as a big array, and a of 4 is some small part of that. So how do we get that stuff from the good data that's in memory into registers so I can operate on it and stuff it back there? That's what we're learning today. Okay? These are called data transfer. So I'm transferring between memory and registers. That's what the next couple things are. But it's all about memory. Really, registers are the nice, handy thing I have as scratch space. But the real deal is that memory is where all the stuff is really living, right? You fill memory, then you bring locally registers, but put it back in memory is kind of where it happens. So you think of memory as the big guy. Memory is the 600-pound gorilla here. So here is the 5 parts of a computer. Okay? You may have not seen this slide before. We often start showing on the first day. I'm showing you now on the, what day are we on? 8th? 6th day? 6th lecture. These are the 5 parts of a computer. I think it'll come up again. In a traditional von Neumann architecture, I have 5 big parts. This is so fundamental in 61C that I believe this is TAT-worthy. If you guys want to actually go and put a little, I would suggest henna, but if you want to go hardcore, go the hardcore thing. Processor, memory, I/O. That's the world, okay? Processor is 2 pieces, the brains and the brawn, control and data path. The memory is where the stuff gets stored. And the I/O is how the computer actually, it's kind of the wheels meet the road, okay? So what we're talking about is these 2 operations. Store, and by the way, registers live in the data path. So we're talking right now about a store and a load, And we're talking about relative to the big 600-pound gorilla, memory. So if I say I'm going to do a load, what am I loading from? I'm not loading from registers into memory. I'm loading from memory. It's always, memory is the first part of the direct object. So I load from memory. I store to memory. So data transfer operations, we saw that. Okay, so here's the bottom guy. Remember, load from memory, okay, to the registers. But the memory is the first guy that you talk about. Okay, so registers, I know I have this address. I know I have $0 to 31, basically 5 bits to allow me to address my register. That's not special. We've seen that before. Memory is a little harder. Because memory, Dan said, think of the abstraction of a really large array. Okay, so that's fine. I got that. So how do I specify where I am in that array? Probably a nice unsigned number. That'd be nice and useful. Maybe a pointer. Okay? But it's often useful to have, let's say if I have an array, like A, right? A of 10, let's say. Okay. So A is nice. We know that array A means A is really a pointer to the first element. We said that before. Okay? What if I want A of 1? Or A of 2? Or A of 3? If I want A of 1, but I only allow you to have a pointer, then what I have to do is take A, add 4 to it, and then look up what that new A is, and that's A of 1. Take A, add 4 to it, and now that's A of 2, right? I have to keep moving A across. Now remember I said you can't really move A, but I have to keep whatever local variable is holding what that pointer is, pointer plus 1, pointer plus 2, which is really translated to bytes, pointer plus 4, pointer plus 8, pointer plus 12 for the next successive guys in the array. But that's, see how annoying that is? That's costing me a performance hit because I now have to have 2 instructions. One is the add the pointer to pointer plus, pointer equals pointer plus 4, and the next one is use one of the load from or store to memory guys to get it. It'd be much easier if I actually allowed you to specify an offset, which means how many bytes away from the pointer I'm going to add to the pointer before I actually go to that place in memory. That's going to save me 1 instruction, and I like that. Okay? So, this is going to require our third type of instruction. We had the adds and subs, which are RRR. We had the immediates, which was RR constant, or RR immediate. This is a strange guy, because I want to specify register to receive it. If I'm loading from memory into a register, I need one R to tell me who's going to get clobbered with the new data. I need another register to tell me where's the base pointer, where's the array start, and I need this constant. And you say, but Dan, I already have this immediate thing. Couldn't I just use that? We're going to see how that's actually stored. But essentially, I may or may not have to use another special case for this. It seems like we could almost use that previous case of the R with the constant offset. That sounds like that's a pretty good deal. So let's see if that'll work. And we'll actually reveal the sheets later. But it sounds like that we can maybe squeeze that into the same format as the immediate guy. So I have, the idea is register to receive it, register where the pointer is, and the offset. And here's how I write it, by the way. You're going to see it like this. So here is T0 in parentheses. That says T0 is the pointer to the beginning of the array, and 8 is the number of bytes of offset I add to T0. So if this is integers I'm looking at, this is really, and T0 is A, this is really A of 2. Does that make sense? Because if the offset was 0, then that means A of 0. If this offset is 4, it's A of 1. If the offset is 8, it's A of 2. Okay? Remember, I have to keep multiplying by 2. So, here's the syntax. Here's how it looks in text. When it actually turns out to be zeros and ones in the binary representative, we might be able to reuse the immediate format for that. We'll see that later. So here's the format. 1 is the operator's name, which is here's load word or store word. 2 is the guy receiving it. So that's the same as before. But the first guy is always the guy getting it, getting clobbered. And then the 3 and the 4, 3 is your offset, and 4 is your pointer. 1, the instruction name is called LW, because we're loading a word at a time. That's very, very useful. If you had to go and load every single of the 4 bytes of an integer, that's ridiculous and annoying. So you're going to grab this word at a time, because it takes a long time to go to memory. So when you're there, you might as well get a lot while you're there. There's a question. Correct. So 1 is going to be LW. Next slide has it. LW. T0 is the guy getting clobbered, receiving the data. 12 is my offset. S0 is my pointer. Just like that slide. LW, T0, 12, S0. Okay? People always ask me, and I will jump at you already and say, why can't you put a register instead of 12? What if I want to have a register be the offset? So it's that register plus that register, and that becomes it. That can't be done. This is a different format. This is just that's something you say, oh, let me make MIPS version 17. Okay, you can suggest that as another MIPS operation. Remember, the idea of MIPS is having things solid and small. If you wanted to do that, you'd actually could just explicitly break it down to be S0 equals S0 plus whatever register you wanted to have here, and then you'd be S0 of 0. So if you wanted to actually add two registers together, instead of having a 12 there, have a register there, you can just add them already and clobber the guy and then have, put it in a new register, T0. Well, T0 is getting anyway, but put in T1 and have that be there. There's a question in the back.
Why do you decide to use the 12 parentheses format as opposed to just making argument like they do with that? You know what I mean?
I see what you're saying. Why do they do the parentheses thing? I think because loads are a little different. I think it's kind of, it looks a little bit like an array with some parentheses, these squares, curly things. It's just the text. Nobody does this. 99.9999% of assembler is written by a compiler. So people don't really look at this stuff. We're going to make you hand author some assembler, but for the most part, compilers are putting that, nobody really cares what that is. That's like an abstraction below what it really is. Who cares about it? Another hair in the back. Yes, Christian. Say it again? A great question. Great question. How many bits is that offset? We're going to see that later. Right now, I kind of revealed a little bit more than you need to know that there's I got a space for you right in here, my friend. That there's a limit to all these things. I want you to think about it. So think about, I got to specify at least 5 and 5 for the two registers. Make this right in front. Yeah, got you there, buddy. You don't want it there? No. Wow. Oh, I love it. Come over. Ian, come back. No. But think about it. You cannot. The max it could be is what? The max forever. I got 10 for the two 5s, the two registers, out of 32. That's 22 left. I got to have some number of bits for my instruction. So however many bits for my instruction, that my left is kind of the biggest it could ever be. So you're already trying to think about how big it could be. So anyway, blah, 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 blah. It goes into S0. S0 better be a pointer. Adds 12 to it. Goes to that memory. So grabs it. Where's that? What's S0? Here's 32 bits. Add 12 to it. Okay, that's a new value. Go to memory. Take the long walk. I'll tell you, this is going to take a long time. Way more than one clock cycle, by the way. Remember the adds and the subs? One clock cycle. This thing is hundreds. CPU is going like, come on, I got better things to do over here. Meanwhile, nope, I'll get there. There's an old show called the Carol Burnett Show where they had Tim Conway. He walked like this. This is the guy going to memory. Okay? He goes and gets it, takes 100 or more clock cycles to come back. Then I got the value, and all of a sudden T0 and clobber T0 with the value of what was in the memory location. Question?
So you keep saying that offset is in bytes.
Yes, offset is in bytes. Did I say 12 bits? I'm sorry. I have 32 bits representing my pointer. I have 12 counting in bytes, but this is byte addressed. So I'm taking some number, adding 12 to it, and that is my address in bytes. So 12, I have raw bits. I have 12 in raw bits. I make those two numbers. I got another 32-bit number in raw bits. Each one of those bits corresponds to a different byte in my array. Yes, question?
Could the offset be another value, like we don't know where we're trying to get to, could we expect it for a variable?
That is the question I try to get there. You can't put a variable there. Got to put a number there. Got to put a number there, buddy. Yes? That's a very good question. Can you be productive while you're waiting for that? The answer is you can be clever about it. You can be clever about trying to reduce that time by having a local copy stored in something called a cache, we'll see. You can also be clever about it by having another instruction that's not doing a memory thing be launched as parallelism at the same time. So I'm able to do some adds over here as long as they're not dependent on the value that I get back into T0. If they're not using T0, I can go ahead and do those things. That's called out-of-order execution or multi-threaded execution. I can do a lot of those things to be very clever about it. We'll see all those things in this class. But yes, you can be smart about it. Good question. Data flow is right to left, right? Just like it always has been. Yes? Yes? Yes. You get the values on the right, like z equals x plus y. X plus y is on the right, as you're looking at it. X plus y is on the right, and then you stuff on the left guy. So T0, the leftmost guy, gets changed. Data flow is from right to left, right? Now, here's where it gets weird. Store word is exactly the opposite. So, what am I storing? Am I storing into, where? I'm storing into what? Into registers? No, it's always storing into memory. Memory is the first thing you got to say after these instructions, because memory is the big guy on the block. So I'm storing into memory. So watch the load and store. There's exactly the same form. All I did was literally take my eraser out, erase the L, write an S, and that's my store. It's the same format. But here's the annoying thing. That green guy is the annoying thing. You got to remember that the store word has the data flowing going the other way. Okay? It takes T0, extracts the good 32 bits, then it also has to, that's in one hand. The other hand, it has to take the S0, the pointer, that's the base register, add the offset to it. Now I have exactly where it's supposed to go, make the slow Tim Conway walk over here, find the place with my right hand, and stuff it in there with my left hand, and I'm all done. Okay? No register gets affected by this. At the close of a store word, no register gets changed. Memory gets changed. This is the first operation that does not change a register. Every other one, add I, sorry, no sub I, and load word. Every one of them affects a register. This is the only one to affect memory. No register is affected here. You're going to see that in the data path series where you have different cycles, and the guy who's supposed to change registers goes to sleep because there's nothing to do for stores. They don't change any registers. So the guy whose job it is to change a register says, hey, we're easy today. That's a nice day. Okay? Questions? This isn't that hard. Just two things. Okay. So, yeah, go. Oh, there's one? I'm sorry. Did I hear me? Yes. Wait a minute. Yeah, it's hard to see it in the back. Let's go back.
What happens if you do an offset value that's not a multiple of 4?
That's going to come up. Save the question for a couple slides. Thank you for that. So for now, we're going to hope that those are multiples of 4. Let's see what happens if it's not in a slide or two. So here's the key thing. And I've said this before, but this is a nice slide to kind of reiterate it, because I want to make sure that you really all get this point. So the hope is in lecture, if you say it a lot of times, they'll eventually get that. These are just bits we're talking about, folks. They're just bits. There's no connection, as there is in C, with, int x. The system remembers, okay, x is an int, and I know, what's x? Int, I had it written down. In here, there's nothing. If I'm at the assembler level, there is nothing left. All of that overhead, that nice bookkeeping, that x was an int, not there. Okay? In fact, even the idea of x and n's being kind of int names and f1, f2, like float names, you're kind of even naming them nicely. No, not there. You just have $T0 and $S0. There's no, and that's true for everything. And in $T0 and S0 is going to store 4 characters, 32 individual bits, a float, half of a double, an int, an unsigned int, anything. Okay? So, if I say this add, which has 3 arguments, I better assume that those 2 arguments, T0 and T1, hold numbers that make sense to add them. If they held 32 logical values, let's say I decide to use T0 to remember the light switch, whether people are wearing a hat in the first 32 rows of the room, does it make sense to add that? It doesn't. That's not a number. So I'm taking something that could be any 32-bit value of pattern of the hats or not hats, and calling an add on it doesn't make it totally loses the idea that these are 32 independent binary values. So if I have an add, that better mean that the arguments to the add were numbers, because that's all I'm doing to it. You have to remember that, and you is hand authorer or compiler, okay? If you're doing a load word, then T0 better be a pointer. It has to be a pointer, okay? How about T2? What better T2 be? Anything. You could be storing anything in memory. So there's no constraints on T2, the guy receiving that. But if I'm going to T0 memory, you better be pointing to a good place, hopefully that you have access to. Otherwise, you're going to have a seg fault. And it better be word aligned, otherwise you have a bus error. So the answer is, you better assume that these things are the right thing when you make the operation. There's no overhead to help you with that. If you're writing hand-authored code, you got to keep track of a lot of stuff to author correct code. Okay? This is byte versus word. In the olden days, we used to be word addressed. So memory of 0 was the first word, the first 4-byte region. Memory of 1 was the second 4-byte region. But then we said, well, how do you, in that system, how do you access a single byte? I want to write a character to memory and read a character. How do you do that with that? It kind of doesn't make sense. There's no a quarter. How about memory a quarter? No, that's silly. So what we do is if we use byte addressing, then we get the benefit of being able to read and write characters if we want to at any place, and read and write words, as long as it's word aligned. We'll talk about that in a moment. So we get the benefit of both things if we go at the lowest common denominator, which makes sense as bytes. Is that okay? So we're going to work with byte addressing rather than word addressing. Historically, we used to use word addressing. Now it's all byte addressing. But it means the annoyance of always having to add 4 and having Dan always remind you about this add 4 whenever you move to the next guy. Because it's always byte addressed. And that's the address of the word there. So let's do some code. Here we go. This is our first bit of code. By the way, it's going to be a little piece where you do a little homework here. So make sure you get a little piece of paper or some laptop scratch space out. Okay, here we go. So I want to do A of 5 in C. I want to say G. Actually, you had no idea how to translate that to MIPS. Right now, you can. You say, that's easy. G and H, where are they stored? Well, they're in S1 and S2. How about A of 5? Okay, A. What's the base pointer for A? I got to tell you what that is. S3 is the base address of A. Okay? So, by the way, here's what's interesting about this. Note that A is not stored in memory. This example has A not stored. A is only in a register. So already you're saying, oh look, guess what? A doesn't have any memory spot where I can change A and now A points to something else. Why? Because A is an array. That's kind of helping you start to understand why A is different than a pointer. Right? A is also a pointer because it points to the first place, but it's in register, not in memory. Because there is no place in memory for A. I've said that before. I'm just saying it again now. It's in a register. We'll hope that it's in there and lives there for the rest of it. Otherwise, I can't store it to memory because I have no space for that. I don't have a place for it. I might be able to have space for it, but I don't store it there. So I have my A. What's my offset? Well, I've said before, we're counting by bytes at the memory level, but A of 5 needs pointer arithmetic to say it's an int are 4 bytes wide, therefore 5 times 4 is 20. My offset is therefore 20. So LWT0 20 S3. Okay? That's what G equals H plus S5 is. That's the first part. That's getting the A of 5. And by the way, this comment is really useful. You're going to see as we write more and more MIPS, having a comment like this is so helpful when you're reading this. Okay? In fact, I've even given midterms where I say, look, here's 10 lines of MIPS, but the point of this isn't to ask about what this MIPS does. I want you to see if you can fill in the blanks down here. So we really ignore the MIPS, read the comments, because I want to get to the point where you can read the comments and then do the same thing the MIPS does. So I don't often make you read every line of MIPS. Sometimes I just say read the comments and do the same thing. And you can do either one. You could read the MIPS or read the comments, but comments to me are easier. T0 gets A of 5. I get it now. I don't have to kind of say, oh, a learned word, what's the order, what's the offset, right? No. T0 gets A of 5. It kind of makes sense, right? And then I've got to obviously add that to H to put it into G. And that's the bottom line, which is add. Okay, questions about this? Not too hard. Just an example of an application of the slide we saw before. So, this is, as I said before, one of the most common errors. I'm going to say it again because even though I say it, people still make it. So, the common error is you forget that if you have any word size element, the next guy is +4, not +1. And we're talking about being word aligned. Remember, for both load word and store word, the sum of those two things. Once you finally go to memory, which is obviously the base address plus the offset, it better be word aligned, which means a multiple of 4. So now we go to the next slide talking about what word alignment means. Okay? So the answer is, in MIPS, memory accesses of words have to be word aligned. Okay? So here's what this means. It's kind of a pretty picture. I love this picture. I'm a very graphical person. This answers the whole thing for me. Things that are aligned, we, by the way, normally count the lowest order byte on the right and then go to the left, so kind of they fill this way, as you would any number. But as I start to write a big number on the board, I start from the right and get bigger with bigger bits on the left, so this makes sense. The last hex address of the memory address, if I actually look at it in hex, better be 0, 4, 8, or C. And this is the value of the guys that are not word aligned, the other 12. Here's a fun question. What is the last, say, 2 bits, if I'm talking about word alignment, in binary? What do these 4 all share as the lowest 4 bits in binary? 0, 0. That makes sense? That's a multiple of 4. I take any random number in binary, just should be a random number, 32 random digits. To multiply by 4, I shift left, placing 2 zeros in the lower end of the thing. When you multiply by 10, you just shift it to the right and put a 0 there. That's by 10. Multiply by 2 in binary, you shift once and put a 0 there. By 4, it shift twice and put 2 zeros. Like multiply by 100, right? Any multiple of 100 is going to have 2 zeros in the 10s and the 1s column. And the multiple of 4 is going to have 2 zeros in the 2s and the 1s column. Okay? So, anyway, every load and store word has to be word aligned. Therefore, in hex, the lowest hex digit is either. But the funny thing, it's called hex digit. So we call it a bit because it's a binary digit. So I kind of want to have it's like bit. So this should be the lowest hit, right? Should it be the hex digit? No, nobody think that's funny. Okay. So that's important. So now you're going to say, Dan, I got it. But last time you kind of stung me on my peer instruction because I voted that if you had any expression that had more than 16 variables, I couldn't do that. I actually couldn't have any expression that literally had to add. What if you have in C, sum equals A plus B plus C plus D, blah, 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 and I have enough letters that I exceed 16? Well, Dan, you could break it up into sum equals sum plus A. Sum equals 0, sum equals sum plus A, sum equals sum plus B, sum equals sum plus C. You could do that way. But what if I had something complex that actually required, honestly, to have 16 guys around? And all of a sudden, I realize in my C, as I'm hand compiling this to MIPS, I need a 17th guy. I need to hold 17 things around. Well, what can you do? What else? What could you do? What other scratch space do you have? You have registers. You said, well, Dan, you told me there's 32 of them. You only told me 16, so borrow somebody else. Borrow some from your neighbor. Can I borrow a cup of sugar? Can I borrow a register, please? Thank you very much. Maybe we'll see that there's some more T's. We're going to learn that there's actually some more T's out there. But what if I continue to keep adding more things you need to keep track of? I can go over to memory. Memory is infinitely big compared to my little teeny 32 things I can store. It's infinitely big from the point of view of register. So I might take some registers and, okay, U5, I'm going to use you later, but I don't use you right now. So I'm going to take U5 and I'll move you over one at a time and then I'll put T0 there. And remember this, I have to keep my own bookkeeping, right? Okay, T0 is here. Everybody remembers this. Okay, write this down. T0 is by the line, and then T1 is by the light switch. And you're storing the registers, and you're keeping track of it somehow, into the memory. This, my friends, is called register spilling. It's like you're filling up a cup, and it's just spilling over. Essentially, I'm adding an expression that needs more stuff, and I filled up the registers. So I'm spilling them over into memory. Okay? That's going to cost you a lot in terms of time. Going to memory is going to cost you a lot. But that's the way you can have any expression of any complexity, is you just push it in memory. You say, but Dan, where in memory are you allowed to write to? If my user has requested a malloc and I've given him this whole panel, you can't write here. And I say, that's right. So I'm going to have at least 32 places, and maybe a lot more. We'll talk about where I can store these extra things for my spilling purposes. So that's what register spilling is, and that's why we use it. Okay? And obviously, we keep things in registers because they're faster. I talked about the speed issue, although sometimes I can't keep all things in the 16. Question with the hand raised in the back.
If you put the registers in memory, don't you still need another register to remember where to put them?
That's a great question. So the question for the people at home is, don't you have to use a register to remember where the stuff is? And the answer is yes. We're going to see when I spill, in a case of, say, a procedure call, I might have to spill it, but I will remember where it was. That's exactly right. I'm going to store that to where it is. That's right. Other things? Yes? The word size for MIPS machines is always 4 bytes. Word size has varied historically, but for us in this class and for MIPS machines, always 4 bytes. Okay? Yes, question? So the question was, if you're in a function and you had some variables that are out there you don't need, isn't it just smarter to move them out and make yourself room for it? And the answer is you really want to save gun memory until it's the last-ditch effort. So you usually only ever spill if you have to. That's the idea, optimally. There's some model, which is we'll learn about procedure calls in about a week or so, where you're going to traditionally just spill all your stuff over, okay? Assuming that the cache can help you with the speed issue. So we're going to see another model where you spill all the time and start with a kind of clean slate. We'll talk about that. Yes, question? Sorry, say that for that. But you don't spill things you haven't touched. You only spill the things you're using, if that makes sense. So if I haven't touched T7, what's the point of writing garbage to memory? I only touch the guys that's there. Sorry. What was your question again? I'm sorry, I've interrupted you.
So how do you want to go to memory and get like a chart or a double and add them?
What do you do if you want to go to char? Well, there's load double, store double, and there's load character and store character. We're going to see that as well. And the address is the same. You don't have the restriction on being byte aligned for the character reading and writing. For doubles, you have to have double word aligned. You can't store a double without being every 8. It's a multiple of the size of things you're storing. Okay. So that's the answer to this one. Administrivia. I want to make sure I get through everything. I think I'm a little behind, so let me go through. The midterm we have is midterm schedule. Yay! Thursday night. 7 to 9, October 6th. Anything happening October 6th that's like, is it homecoming or something? Is it? Anyway, as far as we know, there's nothing overlapping, no big election or something like that. We once had an exam on election day. That wasn't so good. Lab 20 is now officially back in 3:30. Thanks to the folks in CogSci who helped us with this. By the way, I looked online, and every single person is in the class. I told the people in the back room I gave them a wink, wink, nudge, nudge, and everybody's in the class. Whether or not they're officially in that section, I just put them in some section, put them in the class. I don't want to deal with the wait list anymore. Everyone's in the class. Wait list is 0 people today. Yay, everybody's in the class. Yay. And woo! And there was much rejoicing. Yay. And people have asked on Piazza whether you can get checked off on another lab, and the answer is sure if there's room. If there is, like, the lab TA and any lab assistant are sitting idle, fingernails, come on in, get some help. But if they're scrambling to do that, then don't do that. So go to a lab that's lightly covered and ask the TA, do you have time to check me off? And if they say yes, then that's cool. Otherwise, uncool. Okay? Yes, Anirudh. The lab extra credit affects the overall course grade. Yeah, the lab extra credit is part of the lab grade, and that lab grade can be more than the percentage for labs. I think labs are like 5% or something. That lab, your overall, if you keep extra credit, can be a 6%. You'll get the 1 extra percent or something, whatever that is, whatever the percentage it is. But yes, it's course grade. Okay? And TAs, anything else to mention? We're just about to hire readers, and our readers, we have some all-star readers we're putting up to there, so they're going to be getting your homeworks back to you very fast. So we're going to get that rolling. Yes, question? Lab checkup and office hours, it's up to the TAs. What do you guys want to do? I see a nod of a yes here. Yes, yes. Thumbs up here. It sounds like you can get lab checkups and office hours if you can't finish in your lab. But optimally, you get finished in your lab, but if you spill, can you see lab spill, check out spilling? No love. No love. All right, give me some. Yeah, go ahead. Sure. And we're back to spilling. Let's go back for a second. Go ahead. That's a great question. What can I do about the fact that I have 5 writes in a row? Okay. Turns out that I don't want to reveal and scoop on the cache stuff too much. So it turns out that at this level, it's going to take us 500 times. We're going to learn that the cache is going to help us a lot. So I don't want to say more than that because I really want to let this cache be a big splash of how they do that. But the answer is we can. I did mention, so the question, can you be doing anything else? I did mention before that you can launch things out of order and be doing like an arithmetic thing at the same time as a memory. So I did mention that you can't do that if you're smart about it. Okay? All right. Actually, not smart about it. If your system supports that, that's really what I should say. Okay? So far, what we've done today is data transfer and decisions. This is actually the big part of it. So I think, this might be tight on time. I hope we can get through these 7 things. So far, you've made no decisions. You have the dumbest MIPS computer ever because there's no way to make a choice, right? What makes things intelligent is you're making a choice. You're looking at the decision tree and say, I could go left or right. I could either speed through the light or stop at the light. I haven't shown you how to do that. if is the fundamental piece of that in C, right? If is the basic thing that is at the core of a for loop. It's the core of a while loop. If is the basic building block. So I'm going to teach you how to translate ifs to MIPS. That's the first part of that, okay? So the first thing is I need to teach you bad C. So most people agree that if you have labels in your C code, unless you're an expert and you know what you're doing, you're probably writing bad C code. Okay, so they dissuade you from writing labels. But I'm going to suggest that to do the C to MIPS translation, you actually go through bad C. And that makes the next level of bad C to MIPS really easy. So C to bad C, not too hard. Bad C to MIPS, pretty easy. And now the whole C to MIPS is actually easy overall. Okay? So labels are key. You also have the idea of a go-to. Go-tos are actually allowed in C. But again, if you have a go-to, you probably had a go-to a label, that's probably the sign of really bad C, so you want to avoid that. But you need to have labels there because that's the only thing you've got. Get paper and pen ready. You can also use the back of the handouts if you want to do that. Ready? So, this is the first one that you got to see. All right. If condition clause, assume clause is one thing or a suite of things, and then if condition clause 1 else clause 2 can be rearranged into this, what I call bad stank C. Okay, this C stinks to high heavens, but it's good to translate this to MIPS. So here we go. Let's see if this makes sense. By the way, this is valid C, just so you know, but you might not realize you can have a go-to and a label there, but you can. I'm glad that you didn't know that because you're not supposed to know that stuff. So, it's like in, page 200 something. If condition go to L1, now we're back at like the basic, right? This is like writing basic back in 1983. If condition, who's born 83? Only me, okay, Mike and me. Okay, three. Okay, three of us. So if condition go to L1, okay, what's L1? Well, then it's clause 1. And then I fall out of it and I keep going whatever's after that, okay? And that's good. What if there was a clause 2? What if it's not that way? Well, if it's not that, if the condition is false, I don't take the go to and I do clause 2. But then I have to jump around clause 1. Do you see that there? If I didn't have the go to L2 here, right there, I'm doing this for the people on the webcast, then I would do clause 2 and clause 1. But the point is to do either one of clause 2 or clause 1, not both. So I have to have the go to L2 in there, and I also have to have an L1 and an L2. The L2 is critical to jump around the clause 1. The L1 is critical to be able to jump around clause 2. Do we agree that there's a one-to-one mapping between bad stank C and beautiful pretty C upstairs? Thumbs up? Okay. This isn't too hard. This lecture isn't a lot of brain-busting things. Just kind of teaching you how we decided to do stuff. So, this is the first big thing. Branch equal, register 1, label. Wait, what's label? We're going to see that label is going to map to a number. So maybe this is actually the same kind of format as an immediate, right? RR constant. So maybe we can still live with not having to have an exception so far. So I like that idea. BEQ. BEQ stands for branch. Branch means make a decision. A branching point in your decision tree. That's what the word comes from. So branch is, we don't say, that's a branch is, from now on in architecture, branch means an if. That's how you can think. Oh, branch means a decision. I'm making a branch between two options. Take it or don't take it. Take the label or don't take it. Branch equals, BEQ stands for, if R1, register 1, equals, double equal sign, R register 2, this is in C, then go to L1. That's the exact one-to-one mapping of what this BEQ stands for. So, that first line, which was this guy, if condition go to L1, is exactly that line. That's a branch equal. Isn't that nice? Very easy. So that's pretty cool. You're going to guess what happens if not equal. That's obviously there too. And BNE stands for branch not equal. Okay? I might have called this BE and BNE, just for the E for equal, but they do 3 characters for these things. Okay? These are what they call conditional branches. We're going to see unconditional branches, which means you just do it unconditionally. You do it like the love of a child. It's just there, constant. You can have an unconditional branch, which means just do it regardless of what some condition is. Just do it all the time. A conditional branch means based on the condition of the equality of the 2 registers, go there or not. Okay? So far. People often say, well, how about comparing a register to a constant? Maybe we'll see if we can table that until that comes up. So, here we go. Unconditional branches are called jumps. Just says go there. It's like a go-to. Just says raw go-tos is what those are. And those are jump label. Just go all the time. No questions. Not even any registers as arguments. Just go there. Now, you're going to say, but Dan, you told me in MIPS to have a minimal MIPS footprint. I want to have the fewest number of MIPS operations. I want to have the minimalist Philip Glass model. I can do a jump label by saying branch equals 0, 0. 0 is always equal to 0. Why don't I just do that one? Okay? Great question to ask. The reality is, remember that Christian's question about the number of bits for things you were asking earlier? Well, BQ00 means that that's 10 bits that are used up for always 0. That means the label bits, I can't use as much. I can't go as far because the number of bits for how far I can go is smaller. So by saying jump, I have more bits to be able to jump to. I can jump farther. So I'm just going to give you a little taste of why I have to apologize to all of you who are going to be implementing this, that now jump is a different kind. I now have to introduce a different kind for an engineering reason, because branch doesn't let me go far enough. Okay? So jumps are special, go there all the time, just the same semantically as BEQ00 label. It's just I get more bits for label if I don't have the 00 there. Okay? So far? So, here we go. Compiling C into MIPS. If I equal J, F equals G plus H, else F equals G minus H. Go. Write it down. I'll turn the lights on. Now you can't see it. That's good. I'll turn the lights back off. Maybe there's a middle. Is there a middle setting? There's 2, a happy medium? No. 2 watches the screen. All right, and we're back to 3. And action. Sorry for those of you who are writing in the dark. If I equals J, F equals G plus H. Otherwise, F equals G minus H. And those of you who are clever might notice the things that happened either way and take those out of the branchy part. Just throwing that out there. And here's the register mappings for all the variables. I'll just talk over this. This is the kind of thing we ask you to do on exams, but just harder than this. This is obviously the first one you've done. This is exactly the kind of thing you could have in midterm and final. Here's some C, translate to MIPS, pretty standard. And reverse. Here's some MIPS, go to C. So we'll see that as well. Make sure we have enough time for the peer instruction, so I'll give you about 2 more minutes. And here's the flow chart if that helps people to see if you're a flow chart kind of person on the top right. See if you can do it without referring to the slides and the other pages too. See if you can kind of remember the BNE, the BEQ, how that works. Getting this stuff into your brain helps a little bit with speed when you get to the exam. That said, you will have a study sheet on the midterm. So the midterm we always have in 621C for every year for the last 10 years that I've been familiar with. We've had a single sheet that you bring to the midterm. You write it by hand on both sides, and that's kind of a way for you. They've proven that to have you go through your notes, research has shown that if you go through your notes and pre-process them to create the study sheet, learning will happen in just building the study sheet. It's really cool. Just the process of kind of regurgitating it for your own optimized, distilled way is a great way to study, just building the study sheet. I still have my study sheet from my sophomore class in circuits. That's what I refer to. I lost the book. I still have the study sheet. Answers all my questions. I love it. Feel free quietly to compare with your neighbor to see how you're doing if you want to, or work together. It's about a team thing. And there is, as you're guessing, no single right answer to this. There could be a lot of pieces of code that correctly and validly translate this to C, into MIPS, I'm sorry. And I think the answer's on the slide, so if you want to just compare with the slide, yes, you can look at that. All right? A lot of people are talking, so let's look at it. Here's what I've got, which is, I start with my branch equals, if I equal j, go to something called true. I labeled my thing true. So it's helpful for me to know that if that's equal, then I go to the true part of that. If it is, then f equals g plus h. And there's my S0, S1, S2. Otherwise, I fall through to the subtract, right, with the else clause, which is subtract S0, S1, S2. I kind of did it nicely, so just write S0, S1, S2 very nicely. Then I've got to jump around the true statement. That's the only thing that people often usually get wrong. You got to jump around the true statement, go to fin, and fin is the end of that. And that between the BEQ and the true, those 4 lines, that encompasses the one line of C. So you're seeing, as you saw before, that often a single line of C becomes many lines of assembly. So if you look at the total lines of code you write, and then use a compiler, look how many lines of assembler, it's often much, much longer. Very, very rarely is it fewer, unless you have a lot of comments, and that's counting for word count or something, or line count. But almost always you're having more code in the assembler size than you have in the C side. Okay? Questions about that? That's not too hard. Yes, right there. How does it store true? Well, in the assembler is the word true. So if you're writing assembler.s code, it will have true colon that stuff. How that goes to the next level ones and zeros, we'll talk about. That's a little bit more complicated. That's a little later in the day. But for now, in the assembler, it is just the word true. It's stored there as a valid ASCII part of the assembler. And you can come up with any name. There are some constraints that you can't use, like underscore something, because that's used by the system. But in general, you have full flexibility for that, yes. All right, good. Peer instruction with just exactly the amount of time left. Here we go. This is a quiet one. I'm going to launch this guy now. And feel free to vote in whenever you're ready. Takes me a while. I hope I got web access. Uh-oh. Let me see if I have web access. I hope I do. Come on, CNN, come up. Yes, I do. Okay, we're back. Good. So, yoink and yoink. Okay, I want to translate the following line. Star x equals star y into MIPS. X and y are pointers stored in S0 and S1. I use the color. Hopefully, those of you who are not colorblind, the colors can help you with this. T is another color, which is blue. And I'm going to boil this down to one of 5 possibilities. A means, either 1 or 2 does the thing. And B is either 3 or 4. One of those 2 guys is the answer. C is definitely 5 and definitely 6. D is definitely 6 and definitely 5. And E is definitely 7 and definitely 8. So register in. Take your time. This would be the kind of question we do in an exam. It's a little too easy, obviously, because this is the first thing you're doing. But another, translate this guy to MIPS. What happens there? Let's wait till we get to at least 200 before we let you people talk to your neighbors. The homework is now pushed to Sunday per your request, so don't forget that one. Don't panic to kill yourself to get it done today. Yes? Airbus is slow. Okay. Well, I'll keep it up. I'll try to keep it up. I'm sorry? The first project had Project TA, Project 1. When is that going up? This coming, you get posted by Sunday. Love it. Thank you for asking. Okay. I'll let people still vote in, but don't change it until I set the next vote. Talk to your neighbors now. Those who haven't voted, still try to vote in if your airbus is slow, but talk to your neighbors for a minute. Try to figure it out. When you're ready, vote in again. We're almost out of time. And this was too easy a question. Oh, numbers are going down. Maybe it wasn't so easy a question. Give me 200. We can. All right. Okay, let's click it out, close it up, click it up, please, if you can. And I give it 3, 2, 1, plus 200, and it'll just get in there. All right. So let's gather for a second to display. You found this to be far too easy, I think, overall. And C is the right answer. What we're doing is we're borrowing, going into where y points, if I move this away, grabbing the value, which is what 5 does, storing in a temp guide, T0, and then reversing it and putting that into S0. So it's really grab from red to blue, then blue to red, blue to green, and that, my friends, is 5 to 6. So, in summary, you now have a couple new instructions. You're feeling more powerful. You can write pretty complicated MIPS programs. Folks, have a great weekend. Enjoy yourself.